I'm Norman Wahlberger. Today we're going to look at reflections in universal hyperbolic geometry, and we're going to relate them to matrices in linear algebra. And this is going to give us a very nice connection between points and algebraic objects. So I remind you we have a physical or geometrical definition of reflection in a point. Here's our unit circle or a null circle. Here's a point A. And how did we define reflection in a point A? Well, suppose we want to reflect this point B. Then what we said was that we were going to draw a line through B which meets the null circle in 2 points. And then we were going to draw the lines joining those 2 points and the point A and see where the other 2 points that those 2 lines meet the null circle are. Join them up, we get another line, and then that meets the line through A and B in the point C. So that's how we go from the point B to the point C. That's reflection in the point A. So we're going to start today by observing that this kind of operation is really defined by what happens on the null circle. If we know that the image of these 2 points under reflection is the opposite points, then we know where a line like this is reflected to. So it's really the effect on the unit circle that we want to analyze. Now if the point A is inside the circle, like there, then this reflection in the point A sends this point to that point, in fact interchanges these 2 points, interchanges these 2 points, interchanges these 2 points. The kind of an involution on the circle. And if we know this involution on the circle, we can find the reflection of an arbitrary point even if we don't know the point A. So suppose we wanted to reflect this point, but we didn't know where the center of this reflection was. But we did know that this point was sent to that point, that this point was sent to that point, and so on. Then we would know that this line here would have to be sent to this line here, and this line here would have to be sent to this line here. And so that unambiguously tells us that this point would have to be sent to that point under the reflection. Here's another version of that picture where the point A is outside. If we have the point A outside, then the reflection in it will interchange those 2 points, interchange those 2 points, those 2 points, those 2 points, those 2 points. We're just looking at lines through A and where they intersect the circle, generally in 2 points. In this case, there's sort of special tangent situations. These 2 lines here meet the circle only in 1 point, tangentially. And so those are fixed points under this reflection. The action on the unit circle keeps these 2 points fixed. And of course those 2 points happen to be on the dual line of A. So this is what we want to do. We want to study a reflection in a line A by concentrating on what it does to the circle, the null circle. So we're going to only focus on null points for a while. So let's consider point A, a line through A meeting the null circle at 2 null points, alpha 1 and alpha 2. And each of these is given by a proportion. That's our projective parametrization of the null points. And I remind you that here's the formula for it. This is an all-important formula for the point on the circle, or the null point, associated to the proportion t to u. This is our extension of the Pythagorean parametrization. And I remind you of an important theorem that we've already talked about, the join of null points theorem. The theorem that tells us what this line is that's joining 2 null points. So here it is here. The line alpha 1, alpha 2 is given by this triple. u1, u2 minus t1, t2 is the first coordinate. t1, u2 plus t2, u1 the second. u1, u2 plus t1, t2 the third. I remind you that's the red bilinear form. green bilinear form, the blue bilinear form. Okay, so the information that the point A lies on this line is that this times x plus this times y minus this times z equals 0. That's our condition for this point to lie on that line. And now let's look at this condition and rewrite it by grouping all the things involving t2 together and all the things involving u2 together. So the things involving t2 are, well, there's a minus t1x there, there's a u1y there, and there's a minus t1z there. And the things involving u2, which are all the other things, there's a u2 times a u1x, a u2 times a t1y, and a u2 times a minus u1z right there. Well, if this times this plus this times this equals 0, it means that the proportion t2 to u2 is the proportion this to minus this. And what is that? Well, so I've rewritten that there. That's t1y. I've just rewritten it a little bit. Group the u1x and minus u1z together like that. And then minus this is over here. t1 times x plus z. It's minus that. Minus that is minus u1y. So what is this telling us? This is giving us a formula for the reflection in the point A. It's telling us that if we have a point A and we have one null point, alpha 1, then the reflection of that null point in the point A is this second null point, alpha 2. And it's telling us how to get the proportion of that second point in terms of the proportion of the first one and the coordinates of A. So this is a formula for t2 to u2 in terms of t1 and u1s and x, y, and z, the three coordinates of A. This is going to be a very important formula for this talk. So we can give it a little name. This is going to be the star formula. This is telling us what the reflection in a point A is very explicitly in terms of the projective coordinates on the null circle. Now I want to work with that formula we've just written down, but I want to work with it in the framework of linear algebra. So I have to remind you of a few basic things, elementary linear algebra. So we're only going to be working in 2 dimensions, so we're only going to be talking about vectors and matrices with 2 rows or 2 columns. So if you're a little bit weak on linear algebra and you'd like to learn a little bit more, I recommend my series Wild Lin Alg. And in particular, the lectures 6 and 7 are a review of matrix multiplication applications of 2 by 2 matrices. That's all what we're going to be using at this point right now. Later on, we're going to be talking about 3 by 3 matrices as well. But for this lecture, just 2 by 2 matrices. So let me remind you of some basic facts there. This is ordinary affine linear algebra. A row vector is a little vector with 2 components, say x and y, in round brackets. A column vector, a little vector like this written down, also with 2 components, again in round brackets. We sometimes call this a 1 by 2 matrix because it's got 1 row and 2 columns. And this is a 2 by 1 matrix because it's got 2 rows and 1 column. We always talk about rows first and columns second. And here is a matrix, a 2 by 2 matrix, which is just an array of numbers with round brackets, entries A, B, C, D. All the numbers are always rational numbers, right? For us, numbers are always rational numbers. That's the preferred arena in which we work. Real numbers are not anywhere in sight, so-called real numbers. Okay, what do we do with these things? Well, we can add them. We can add two row vectors, we get another row vector. We can add two column vectors, we get another column vector. We can multiply them by scalars. So we can multiply a vector by 3, which just amounts to multiplying each of the entries by 3. The more interesting operation, however, with matrices is matrix multiplication. And if you haven't seen that at all, it's a little bit tricky the first time. So if you haven't seen it before, I want you to think today that matrix multiplication is built up from the product of a row vector with a column vector. That's the essence of multiplication of matrices. So if we have a row vector xy and a column vector lm, then by definition, the product of these two in this order, with the row vector on the left, the column vector on the right, is this 1 by 1 vector, which is just a single number, and it's x times L plus y times m. And often it's usual to not put the brackets there and just to write down the number itself. So we sometimes just say that the product of a row vector times a column vector is a number. Now, any other multiplications are built up from that basic operation. So for example, if we want to multiply this row vector by that matrix, we think of this matrix on the right here as being two column vectors, that one and that one. So we can multiply this row times this column, just like that. That's xa plus yc. Or we could multiply it by this column, xb plus yd. And we put those two possibilities down in a vector, right beside each other, just the way these columns are beside each other. So that's the product of a row vector times a matrix is another row vector. Another possibility is to take a matrix and multiply it on the right by a column vector. In that case, we think about this matrix as being two row vectors, one on top of the other. And we think about this product as being multiplying this row vector by that column vector. So that's AL plus BM. There it is right there. And then the other operation, CL plus DM, right there, one on top of the other, because these are on top of each other. Well, if you got the hang of that, then this sort of more fancy version is not too hard. Suppose we have two 2 by 2 matrices. How do we multiply them? Well, the trick is to think of the left matrix as being two row vectors, one on top of each other, and to think of the right matrix as being two column vectors, one beside each other. Then there are altogether 4 possible ways of multiplying a row vector on this side with a column vector on this side. So we could do this row times that column, that would be that number there. Or we could do this row times that column, that would be put over there. Or this row times that column, which we put down there. Or this row times that column, and that's put down there. So those 4 possible ways of multiplying a row of the left by a column of the right makes a new matrix, and that's the product of these two matrices. And so the main thing to know about this operation is that it's associative. So that means, for example, if you have 3 matrices, this one, and another one, say call them x, y, and z, then if you multiply x, y together first, and then multiply that on the right by z, that's the same as multiplying x by the product of y and z. And if you've never seen that before, make sure you check that at least in some special cases and see if you can see why it's true in general. Okay, so that's matrix algebra in a nutshell in the 2 by 2 case, or in other words in 2 dimensions. Here in hyperbolic geometry, we are needing something which is a variant of this. A variant which is not too often discussed in linear algebra courses. This is really affine linear algebra, but there is also another version which might be called projective linear algebra. And that's actually what we are going to be needing. So we need to go outside this rather familiar realm to something a little bit different, not too much different, but we want to projectivize what we've just said here. So let's have a look at projective linear algebra. So what is projective linear algebra? Well, let's just stick with the two-dimensional case. So here is two-dimensional projective linear algebra. There are also row vectors and column vectors and matrices, but they're a little bit different. They are projective row vectors, projective column vectors, projective matrices. What do these things mean? Well, the projective adjective is telling us that the quantity is unchanged if we multiply all the elements by a non-zero number. This is the same property that a proportion has. The proportion 3 to 2 is the same as the proportion 6 to 4 or 9 to 6. If we multiply both elements by the same number, we get the same proportion. So we want to do linear algebra here with proportions. And that's exactly fitting our framework, right? Because points and lines are in fact proportions. So that's very natural that we want to do linear algebra with proportions and rather than vectors. So a projective row vector will be denoted by a pair xy enclosed in square brackets. But there's not going to be any comma. So a projective row vector is a pair of numbers in order with square brackets. The square brackets are telling us that this is a projective object, meaning that by definition the vector xy is the same as the vector lambda x, lambda y, provided lambda is a non-zero number. And I note that there's no comma here. In this matrix theory, we don't have commas separating the entries, they're just arrays. Similarly, we have a notion of a projective column vector, notion of a projective matrix. Now, addition of these kinds of things are not defined, at least not immediately. So it doesn't make sense to add two projective column vectors. But multiplication is well defined. What does that mean? Well, for example, 1, 2, 3, 4. This is a projective row vector, that's a projective column vector. Now, if these were ordinary vectors, we would multiply this row vector by this column vector to get a 1 by 1 matrix, or a number. So that number would be 1 times 3 plus 2 times 4, that would be 11. But here in this projective setting, we're going to put square brackets around that, and we're going to think of that as being a projective vector with one component, or a matrix, a 1 by 1 matrix. We're going to think of that as being a 1 by 1 projective matrix, which means you're allowed to multiply it by any non-zero scalar. In particular, you could divide by 11, so this is the same as 1. That's a bit trivial. Here is an example of a matrix, projective matrix, times a column vector. If they were ordinary objects, we would multiply them this way. It'd be 1 times 3 plus 0 times 5. The first entry there would be a 3. And then minus 1 times 3 plus 2 times 5. That's minus 3 plus 10. That's 7. That would be the second entry there. But here, the final result is a projective column vector, meaning that we're allowed to multiply that by a scalar. And that makes sense because we're allowed to multiply this by a scalar. We're allowed to multiply this by a scalar. If we multiply that by 5 and we multiply this by 10, the result would be to multiply that by 50. Okay, so it's not too hard to see that this multiplication of these projective objects is also associative. So this is now what we're going to use to have another look at that basic equation, the one we called star, that we defined from the reflection in the point A. Let's have a look at it again now with a linear algebra point of view. So here is our equation star rewritten in terms of two projective row vectors. the original equation was in terms of the proportion T2 to U2. T2 to U2 was this to this. But a proportion is exactly what's being encoded here by this projective vector. Right? The projective vector is such that if we multiply both of those things by the same quantity, it doesn't change. So it's really the proportion that determines that vector. So the interesting point here is that this vector here, this row vector, can be written as a row vector times a matrix where everything is projective. It's the projective vector T1, U1 times this 2 by 2 matrix. So let's check that. Okay, how do we multiply these two things? We multiply that row by that column to get the first entry. T1 times Y plus U1 times X minus Z. That's exactly that. And the second entry is T1 times X plus Z plus U1 times minus Y, or minus U1Y. So this equation exactly encodes what we did before. Now have a look. What are the ingredients here? Well, remember that the point A that we started with, that was the point with coordinates x to y to z. That's what's being involved to create this matrix. So to go from this point, which is a point in our hyperbolic plane, to this matrix is pretty simple. We take the second entry, the y entry, and put it there, put its negative there, along the diagonal. And then the other two, the x and the z, are used. The difference goes there, x minus z goes there, and the sum, x plus z, goes up there. X minus z, x plus z in the off-diagonal places, y and minus y on the diagonal places. So we're going to call that something. That's a very important matrix, this thing here. We're going to call this the matrix of the point A. That's this matrix right here. I just copied it again, and I give it a name. It's M sub A. And if we want to, we'll say it's the projective matrix, because it really is a projective matrix. It's only defined up to multiplication by a scalar. You can multiply all the entries by anything you want, as long as it's non-zero, and it's the same object. So what we're doing now is we're associating to a point in the plane this projective matrix. Now what does this projective matrix do? According to this formula, it tells us that the reflection in the point A sends the null point with coordinates T1 to U1 to the null point with coordinates T2 to U2. And to go from T1 to U1 to T2 to U2 is just multiplying on the right by this matrix M sub A. Now if you have a 2 by 2 matrix, there are two sort of important functions or two important numbers associated to such a 2 by 2 matrix. One of them is the determinant, that's the most important, and the second is the trace. So the trace is just the sum of the diagonal elements. This entry plus this entry, that's called the trace of the matrix, and we see that in this case the trace is always 0, because y plus minus y is always 0. And the determinant of the 2 by 2 matrix is always this entry times this entry minus this entry times this entry. Okay, so what is that? Well, it's y times minus y, so that's minus y squared, minus x plus z times x minus z. Well, x plus z times x minus z is x squared minus z squared. If we take minus that, we get minus x squared minus y squared plus z squared. Or if you like, we can write it as minus x squared plus y squared minus z squared. Now let me remind you that the point A is a null point precisely when x squared plus y squared minus z squared equals 0. So A is a null point precisely when this matrix M sub A has determinant 0. And in linear algebra, determinant of a matrix being 0 means that the matrix is not invertible. It means that one of these rows is a multiple of the other, or in other words, the two rows are linearly dependent, or the two columns are linearly dependent as well. That's the most important thing about a matrix, to ask, is the determinant 0 or not? And here it exactly corresponds to whether the point that it's coming from is a null point or not. So we've done something very important here, in fact. This will have major repercussions as we carry on. So the significance will slowly emerge, okay? But this is going to be very important. We now have a way of associating to a point a matrix. And not just any old matrix, but a matrix which has trace 0. And is otherwise rather arbitrary. Otherwise, any trace 0 matrix can be obtained this way. So to a point, we have a trace 0 matrix. And this trace 0 matrix is satisfying this crucial relation, that it's telling us how the reflection in that point transforms one null point to another null point. So let's just summarize that important thing that we just said in this theorem. Let's call it the reflection matrix theorem. So if T2U2, that projective vector, equals T1U1, that projective vector, times that matrix M sub A that we just defined, then A lies on alpha 1, alpha 2, where alpha 1 is E of T1 to U1, the corresponding null point, alpha 2 is E of T2U2, the corresponding null point. This is another way of saying that if we have these two null points, alpha 1 and alpha 2, then the reflection in A sends this point to this point, provided that these 3 points are collinear, provided that A actually lies on the line joining those 2 points. Well, this is the crucial picture telling us what the role of this matrix A is. The matrix A tells us how to go from this coordinate of that null point to this coordinate of that null point. And it works not just for this pair, but for any pair of null points. So if we choose another line through A, we get another alpha 1, another alpha 2. And then if we multiply this alpha 1's projective coordinates by MA, we would get the projective coordinates for alpha 2. And conversely, if we multiply these projective coordinates by M sub A, we would get this one here. So here's an example. Here's the null circle. There's a point E1 to 2, which is the point 3 to 4 to 5. I remind you that you get that by taking 2 squared minus 1 squared. 2 times the product is the second one, and 2 squared plus 1 squared is the third one. And here's the point A, which is 2 to 1 to 1 at some point, 2, 1. Suppose we want to reflect in the point A, we want to reflect this point to some unknown point there. Suppose we don't know what that point is, we want to know, how do we figure it out? Well, this basic relation here is telling us that T2 to U2, the projective coordinates for this null point, are obtained from the projective coordinates of this point, 1, 2, by multiplying by the matrix M sub A. And how do we cook up this matrix M sub A? We have to remember this. Okay. We take the middle coordinate and put it in the top left. We take its negative and put it in the bottom right. Then we take the x minus the z coordinate, put it down there, and the x plus the z coordinate and put it up there. And then the product of these two is 1 times 1 plus 2 times 1, that's 3. And 1 times 3 plus 2 times minus 1, that's 1. So the answer is that this point here has projective coordinates 3 to 1. In other words, this point is E of 3 to 1. And how do we calculate that? 1 squared minus 3 squared is minus 8. Twice the product is 6. 1 squared plus 3 squared is 10. And since it's a proportion, we can divide by the common factor 2, because we don't like to have any common factors, giving us minus 4 to 3 to 5. That's the coordinates of that point. That's the reflection in A. So we've reflected in the point A. The reflection of that point is that point. This matrix is telling us how to reflect in the matrix A on the null circle. So let's give this correspondence a name. Let's call this the point matrix correspondence. Between the point x, y, z, that's a point in our hyperbolic plane that we've been studying, and the associated matrix M sub A, which is y minus y, x minus z, x plus z. And these are associated. If we know this, we can get this. Also, if we know this, we can get this pretty easily too. So suppose we start with the matrix, say M sub B, and it happens to be P, Q, R minus P. So still of this form, still of trace 0 form. Well, then how do we recover the actual coordinates of B? Well, how do we get x from this? We just take this entry and divide by 2. So R plus Q divided by 2 will be the first coordinate. The second entry, y, we just read it off from here. That's just P. And the z entry, the third one, is this entry minus this entry divided by 2. So it's Q minus R divided by 2. And since it's just a proportion, we can multiply by 2, giving us Q plus R to 2P to Q minus R. So if we start with a trace 0 matrix, then that's the associated point. And this is a complete correspondence between points, hyperbolic points, and non-zero projective matrices of trace 0. The matrices that we get here, the projective matrices, are all non-zero, because there's no way you can get 0, 0, 0, 0, because that would have come from the proportion 0 to 0 to 0, which I remind you is not allowed. So very important. We're connecting with a rather sophisticated branch of mathematics called Lie theory here. Okay, the matrices of this kind are called SL2. It's called a Lie algebra. And it's a very important, simple but important and very interesting subject. There are mathematicians who spend their entire careers more or less studying aspects of this Lie algebra and the associated Lie group. I myself have spent many years thinking about this in various ways. And it's going to be interesting for us. This hyperbolic geometry is going to tell us something about this Lie theory that perhaps we didn't know before. Okay, here's an exercise, the first one, that in this correspondence, the A is a null point precisely when the determinant of MA equals 0. Well, we've already mentioned that, but just make sure that you understand that point. And another exercise, show that if A is a non-null point, then the matrix M sub A, if you square it, you get the projective identity matrix. This particular matrix 1001 has a special role. It's like the number 1 in the land of matrices. If you multiply any matrix by that matrix, the result is what you started with. So it's a little bit, maybe a little bit surprising that that's the case. And it's telling us that the matrix MA is its own inverse. You multiply it by itself, and you get the identity matrix. Okay, so here's now a very interesting theorem, the reflection matrix conjugation theorem. And it says that if you have two null points, alpha 1 and alpha 2, given by these two proportions as before, t1 to u1, t2 to u2, and if A is any point, x to y to z, and suppose it has the property that the reflection in A sends alpha 1 to alpha 2, which in other words we've seen is this property here, that the multiplication by the matrix M sub A takes this projective row vector to this projective row vector. Well, in that case, there's a relationship between the associated matrix of A and the two associated matrices to alpha 1 and alpha 2. Alpha 1 and alpha 2 are null points, but they still have associated matrices, M sub alpha 2, M sub alpha 1. And here's the relationship between those two associated matrices. M sub alpha 2 is equal to M sub A times M sub alpha 1 times M sub A. Now those of you who know a little bit more advanced mathematics will recognize this isn't quite a conjugation. Usually when we so-called conjugate two matrices, we multiply by the matrix on one side and the inverse matrix on the other side. But here the inverse matrix is really the same as the original matrix, so it's easier to write M sub A and slightly more general. Okay, so we want to show that that this relationship between these 3 points implies this relationship between the corresponding matrices for those 3 points. 2 of them are null points. The other one is another point which lies on the line joining those 2 null points. So let's look at an example to illustrate this theorem. I'm going to choose 2 null points. Alpha 1 is E 3 to 2, and alpha 2 is E minus 4 to 5. Here are the homogeneous coordinates of those 2 points. Geometrically, alpha 1 is there, alpha 2 is there. And we can get that by looking at the proportion 3 to 2, and that's the same as the fraction 1.5. So in the y coordinates, that'd be 1.5 about there. Join it to the point minus 1, 0. Where it meets the circle, that's alpha 1. Minus 4 to 5, that's the minus 4 to 5ths down there. Join it, get alpha 2. The line alpha 1, alpha 2 joining those 2 points is obtained by taking the j of these 2 points. There's the j of those. Alternatively, we could have used this f function I defined in terms of these 2 proportions. So f of these 2 proportions would give you the same line. Now I want to choose a point on this line, and let's just sort of find a point by just requiring that this times this plus this times this minus this times this equals 0. So let's say this is 1, so 1 times minus 22, that's minus 22, and then let's say minus 3, so that this times this will be plus 21. So that's a total of minus 1 so far. And then we want minus this times this to be equal to 0 altogether. So this should be minus 1/2. We can multiply by 2 because it's just a proportion, giving us minus 2. Actually, multiply by minus 2 is better. Minus 2 plus 6 and 1. Which is the point minus 2, 6, somewhere up there. 2 over this way, 6 up there. Somewhere in that direction. Okay, we know that this point A lies on this line, so the reflection in A necessarily interchanges alpha 1 and alpha 2. Sends this point to that point, and this point to that point. And we can check that. Here's the matrix M sub A. There's the coordinates for A. So the matrix for it is obtained by, take the middle coordinate, put it there, put its negative there. The difference between the first and the third, minus 2 minus 1, that goes there, that's minus 3. And the sum of the first and the third, that's minus 2 plus 1, that's minus 1, that goes there. So if we take 3 to 2, we multiply by this projective matrix. 18 minus 6, that's 12. And minus 3 minus 12, that's minus 15. And then we can cancel a factor of 3 and maybe multiply by minus 1. That's minus 4, 5. That is indeed the proportion of alpha 2. And you can check that if we take this vector and multiply it by this matrix, well, we get that one there. So what was the theorem here that we're looking at now? The theorem asserts that in this situation, there's a relationship between the matrix for alpha 2, the matrix for alpha 1, and the matrix for A. The matrix for this point, the matrix for this point, and the matrix that we're reflecting in. We're reflecting in this point here, MA. And so this one conjugated by MA is equal to this one. In fact, it works the other way around. It's also the case that if we take this one and multiply it on both sides by MA, we would get this one. So what are these various matrices? Well, there's MA. We've already seen that right there. That's this one here. And how do we find M of alpha 1? Here's alpha 1 up here. So to get its matrix, the middle entry, 12, minus 12 there. The difference, minus 18. The sum of these outside ones, 8. And for alpha 2, the middle one, minus 40, and it's negative plus 40. Then 9 minus 41 is minus 32 down here. And 9 plus 41 is 50 up here. And you can check that when you do this multiplication, this is true. In fact, if you do the matrix multiplication, you'll see that the right-hand side gives you minus this matrix. But minus this matrix is the same as this matrix because we're only in the projective setting. Multiplying by scalars doesn't change things. So that's an illustration of this reflection matrix conjugation theorem. So let's now make the computation to prove this theorem. So what are the ingredients? There's our point A, x to y to z. We're assuming that we have two null points given by proportions t1u1 and t2u2 that are related by, one of them is obtained by the matrix for A multiplying the other. There's the matrix M of A, with A there. Here's our form for a null point. The null point with proportions t1 to u1 is this one right here. So our job is to compute the matrix associated to this one and also the matrix associated to the other one. So how do we find the matrix associated to this? Well, we take the middle coordinate and put it there, and it's negative down here. And then we take the difference, this one minus this one, which is over here, minus 2t1 squared. And we take this one plus this one, and put it up here, that's 2 times u1 squared. Now there's a common factor of 2 here. We can get rid of that common factor because it's just a projective matrix. So we get this matrix here. And now we make the interesting observation that we can write this 2 by 2 matrix as a product of this column vector times this row vector. This is a different kind of product. I hadn't mentioned this before. So here we have 2 rows, and here we have 2 columns. Each of those rows and columns just has 1 entry. So if we multiply this, there's actually 4 products. This times this, or this times this, or this times this, or this times this, and those are the 4 entries appearing there. Now this one here looks a lot like this one, except that it's sort of flipped over and there's a minus sign. And that's exactly what you get when you take t1u1 and you multiply it on the left by this particular matrix, 0, 1, minus 1, 0. Let's just have a look at this times this. That would be 0 plus u1, that's u1, and minus t1 plus 0. So the product of these two is just another way of writing this. The advantage is this is sort of more symmetrical. These two vectors are pretty well the same, except one is the transpose of the other. The transpose is obtained by making a row go to a column or a column go to a row. Now exactly in a similar way, M of alpha 2 is exactly the same formula except with T2 and U2 and T2 and U2. Okay, but now we use the fact that we know that T2U2, this vector, is T1U1 times M of A. So I'm going to replace this T2U2 with T1U1 MA, and this column vector T2U2 with the transpose of this. Now in linear algebra, when you take a transpose, the transpose of this is the transpose of the second thing times the transpose of the first thing. So we get MA transpose times T1U1. Okay, now we're going to just make it a little bit simpler for us by we want to identify this M alpha 1 in there. So we're going to multiply right in here, we're going to multiply by this matrix squared. Because this matrix squared is the identity matrix. So if you put it in there, it doesn't have any effect. So I'm putting it in there twice. Right here, in there twice. One of them connects with this one and this one to give us M of alpha 1, exactly this. The other one multiplies with this MA transpose so that we get this times MA transpose times that other one that we put in times M alpha 1 times MA at the end. That's what M alpha 2 is. That's almost in the right form now. There's an MA on the right, there's an M alpha 1. We want to convince ourselves that this actually is equal to MA. So we just do the computation. There's that matrix. This, well, this thing here is the transpose of MA, which is what? Take this matrix here and we interchange the rows and columns. So yx minus z becomes yx minus z going along the row. And x plus z minus y goes to x plus z minus y there. And then we multiply these three matrices out. And lo and behold, we get y, x plus z, x minus z minus y, which we recognize is exactly M sub a. So M sub alpha 2 is in fact M sub a times M sub alpha 1 times M sub a, just like we said it was. Okay, it's a little bit sophisticated. I hope you've been able to follow it. I hope you can understand more or less what we've been doing. If you haven't done any linear algebra, it will be a little bit challenging, I admit. But I hope most of you have seen some linear algebra before. Now let's just derive two corollaries of this. The first corollary is just an observation that we made during that proof. We calculated the matrix associated to a null point. This was the formula that we obtained. So if alpha is the null point E of t to u, then the associated matrix is the product of this column times this row. And our second corollary is that this reflection sigma A, reflecting in a point A, really does send lines to lines. And by that I mean that if you have three collinear points, say B, C, and D, then the images of those 3 points are also collinear. Okay, so I'm going to just do this a little bit briefly. You can think about this. We'll talk a little bit more about this later on when we talk about 3 by 3 matrices. But right now what we can say is this. The action of sigma A was defined on null points. And we figured out that this reflection in A sends one null point alpha 1 to another point alpha 2 precisely when the projective coordinates for alpha 1 and alpha 2 are related by this multiplication by this matrix M sub A. So this is a linear in homogeneous coordinates. If you think about what this does, not in terms of the projective coordinates, but rather in terms of the linear coordinates or the homogeneous coordinates of the null points, then it's this equation that we've just derived which is the crucial one. Because this is telling us how to go from the matrix of alpha 1, which is built up from the homogeneous coordinates of alpha 1, to the matrix for alpha 2, which has the homogeneous coordinates of alpha 2 in it. And these are all linear expressions of those homogeneous coordinates. And this is a linear operation on those linear coordinates. In other words, if you think of this as a function of the entries of this matrix, it's a linear operator. And the fact that it's a linear operator implies that 3 things that are collinear go to 3 things which are collinear. So I'll leave that a little bit to you to think about. It's a little bit more advanced, I admit. Next time I want to get back to the geometrical consequences of having these reflections around. I want to convince you that the reflections actually preserve perpendicularity, the crucial property. We'll see that they also allow us to define midpoints and bisectors. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.